When we're finding the limits of more complicated trigonometric expressions, oftentimes we want to turn the expression into some form that we do know, that we have figured out, such as the limit as x approaches 0 of sine x over x is 1, and the limit as x approaches 0 of 1 minus cosine x over x is 0. Those are really important, and if there's any way we can algebraically manipulate these expressions to look like this, that can help us evaluate limits. Number 5 is the first example I'm going to do. I can already see that there's cosine squared, there's cosine, and there's sine squared. That's too many different things going on. The top looks like it might be factorable, so let's try that. Cosine x times cosine x gives me cosine x squared. 1 times 1 is the only way to get 1, and if they're both subtracting, then we do get a negative 2 cosine x over sine squared x. This is actually a cosine x minus 1 quantity squared over, well, we could also write this as sine x squared. I'm going to take the quantity being squared out of the limit, so this will be this quantity as the limit as x approaches 0 of cosine x minus 1 over sine x, all of it squared. So I multiplied by cosine x plus 1 over cosine x plus 1. If I do this, then the top will turn into cosine squared minus 1. Maybe we can plug in sine squared for that. The limit as x approaches 0 of cosine squared x minus 1 over sine x times this quantity. Cosine squared x minus 1, that is actually sine squared x. Sine squared x over sine x gives me sine x in the numerator. And at this point, I'm thinking, there is not gonna be a way that I can turn this into one of the special forms. But the special forms are just there to help us. We don't have to turn it into a special form. We just have to manipulate it enough so that direct substitution works. And guess what? You've done that. Plug in 0. You get sine of 0 over cosine of 0 plus 1. That is going to end up being squared. Sine of 0 is 0. And as long as the denominator is not also 0, then we're good to go. Cosine of 0 is 1 plus 1. This quantity will be squared. 0 squared divided by anything, 0. Let's look at number 6. And remember, we don't necessarily need it to look like one of these special forms. These are just here to help us. If in any way we can rearrange it with identities or other algebraic methods and then use direct substitution, we can always do that. So the first thing that I noticed is that expanding this is a possibility, but it would be massive, and it would not help with the fact that the argument of tangent squared here, would not help with the argument that is 2x. So we have a double angle, and then we don't have double angles. Okay, we have squared x squared x. Okay, there's already too many different things going on here. So then I thought, okay, cosine squared x minus sine squared x, is that a specific identity? It looks like the Pythagorean identities, but with a minus sign. Hey, there is an identity that works for. This is cosine 2x. Remember that quantity was being squared, and then we have tangent squared 2x. The tangent really kind of throws you off. It's like, that doesn't look like any of the special forms we were given. So let's continue working with it algebraically. What if we can get it to not be a fraction at all, or to reduce the fraction? 1 minus cosine 2x squared over tangent of 2x, all of it squared. I'm just going to write it like that, so I like it to look similar. At this point, I noticed that in the numerator you have 1 minus cosine squared 2x. Now, 1 minus cosine squared is sine squared. I know that as a Pythagorean identity. And that works no matter what the argument of cosine is. It just has to be the same argument as sine. So if you have 1 minus cosine squared 2x, that has to be equal to sine squared 2x. Now I know I can write tangent in terms of sines and cosines in order to simplify this out. The limit as x approaches 0 of sine 2x quantity squared over sine 2x over cosine 2x, all of it squared. Remember, when we divide fractions, we just multiply by the reciprocal. Sine squared 2x over sine squared 2x is 1. Now you are able to direct substitute 0 into the cosine squared 2x. So cosine squared of 2 times 0. What is cosine of the angle 0? That's equal to 1, and that has to be squared. That would be 1. You can also use direct substitution for inverse trig, but we have to remember what these functions actually look like. To help us with arctan, we're going to remember what tangent actually looks like. Tangent spans from negative pi halves to pi halves, and looks like somewhat of a wave. And there's an asymptote at pi halves and an asymptote at negative pi halves. So if we were to graph arctangent or inverse tan, we would reflect this over the line y equals x. So this, instead of going up, would go over, and this would go this way, which means our vertical asymptotes would actually turn into horizontal asymptotes, which is extremely helpful for these problems. So when we plug in infinity, we're just going to look at the graph we have here, tangent inverse of x. I'm going to rewrite this as a fraction, so the square root of x to the 5th is actually x to the 5 over 2. The limit as x approaches infinity, it just makes it easier for me to see it as a fraction. Okay, if you want to keep it in the root, that's fine. Now we're going to plug in infinity, so tangent inverse of infinity to the power of 5 halves is just tangent inverse of infinity. What is happening as tangent inverse goes to infinity? We have this asymptote and this asymptote. Well, they used to be vertical asymptotes, now they're horizontal asymptotes. This one is pi halves, this one is negative pi halves. So as arctan approaches infinity, we approach pi halves. In this case, tangent inverse of a polynomial, if you have a polynomial, you only need to care about the one with the highest degree, the term with highest degree, holds the significance, okay, and the x squared can basically be ignored because we're working with infinity. So tangent inverse of negative x to the fourth, we're taking the limit of that as x approaches infinity. That would be tangent inverse of negative infinity to the fourth, which is infinity, but there's still a negative in front. So as tangent inverse approaches negative infinity, we are approaching negative pi halves. For number 10, I noticed that sine of m minus pi halves. It reminded me of the cofunction identity that states sine of pi halves minus x is equal to cosine x. But what if it's the other way around? I'm going to take this from the identity and make it look like this from the problem so that we can actually come up with something to substitute. First, we'll start off by saying I'm going to call theta. Now I'm going to do some algebra to this cofunction identity before I even touch the problem. So to rearrange the order, I'm going to factor out a negative 1. And then I'm going to divide by negative 1 on both sides. So negative theta is the same as x minus pi halves. Great. We're going to actually take the sine of both sides, since that's what we were originally trying to find, was sine of a quantity. Sine of negative theta is actually just negative sine theta. Right, that's an odd identity. Negative sine theta is equal to sine of x minus pi halves. Now, if you remember, we decided earlier that theta would be pi halves minus x. So negative sine pi halves minus x is what you get when you take sine of x minus pi halves, the weird flipperoo that we started with. Okay, hey, sine of pi halves minus x, the cofunction identity says that's cosine of x. Drop the negative. So if we're taking sine of x minus pi halves, we get negative cosine x. Sine of m minus pi halves is equal to negative cosine of m. Okay? That's what we just proved to the right. Now, as we use that identity, negative cosine m plus 1 over m, this looks like a special form. It looks like this one. Rearrange it and then use it to solve. The limit as m approaches 0 of 1 minus cosine m over m is equal to 0.